Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone, I'm Madan Musawati, a researcher in the Research and Software Engineering group, and it's my pleasure to introduce Ganesh Gopalakrishnan today. Ganesh is a professor in University of Utah, where he's been for the past 12-13 years. He has broad range of interests, and he's worked on verification, cache coherence protocols, and memory models and whatnot. So today he's going to be talking about making ISP, which is a verification tool for MPI programs, practical. Ganesh?
Okay, thank you, Madan. Good afternoon, everyone. Thanks for inviting me. So this is a great pleasure to give a talk in front of my two PhD students, one former, one current, and they did pretty much all the initial work in this area and continuing work. So what I would like to take you through today is the rationale, the big picture of why we started verification research in this domain that was not very familiar for us, the approach that we have taken for modeling the problems in this domain, then the actual tool that we have running, and I'll do a tool demo also for you, and then we'll actually take you through a miniature development process of an MPI program and how our tool might help in that area. So about 5-6 years ago, we were looking for application domains where software verification can be meaningfully applied, which meant that we needed to have an abundant supply of case studies that we could run our tests on. So by some sheer coincidence or luck, one of the researchers in our area, George, suggested that we look at high-performance computing software, and so we took his suggestion along. And the big picture of what we have done since then has been trying to understand a model of concurrency that exists, and every feature in this world seems to be well meant and well thought out based on real needs, and yet when all these features add up, they are giving us an opportunity to explore a nuance of concurrency and combination of features that are chock full of problems. So I'll take you through how we have managed to step through some of those problems and solve them using formal techniques. So one could look at classical models such as linearizability and things like that, and if you really go back and study fundamental models like that, there will be assumptions made of the interface that each thread sees, meaning each thread has one outstanding method at a given time and so on. And yet one can look at modern programming research where one can see research on asynchronous method calls, where methods are detached and they interact through shared memory and the main computation moves on. Now, a lot of APIs are being proposed for multi-cores going into the future, and there might even be an alphabet soup of APIs that a large application might deal with. So the general sense that we are getting is that one needs to be looking at different models where we may have asynchronous method calls like are found in other systems, but now we have these asynchronous methods calls interacting through message passing, not through shared memory. So this is a new twist. And then there are multiple other features like non-determinism happening in terms of when receives can actually take their send values. And then there are global operations like barriers that can regulate the progress of all the processes. And then the resource availability or lack thereof affects forward progress. This is another feature. There are oodles of libraries. They have various progress properties. So it is an interesting mix of features that we are confronted with. And the hope was for us to deliver a just-like dynamic verifier in this context. So a clear temptation is to go back to a pristine area of computer science and not do anything here, but somehow it will be good to push on and see how far we can go confronted with these problems. So that will be the general feel for the story. And the initial work in this area was laid down by several of my students. So we started understanding this rather large API and trying to understand each of its features. We even wrote a formal semantics for MPI and made it even executable from a C front end and so on, so just to gain some understanding. But we actually felt that we needed actually cannot rely on formal semantics that are built based on just the interface study, but we need to get into the semantics and understand the real exploitable features of the API. So that's where the story is going. So since I didn't know how many people here knew about MPI or not, I have a standard set of slides. So basically, MPI is widely used for cluster computing at all scales. It's a lingua franca of parallel computing. It's called from multiple languages, and multiple processes execute, and the processes compute part of the solution, and they all achieve to solve some real-world problem like explosion modeling or physics. The execution of MPI programs happens on cluster machines of all sizes and scales, and very mature MPI codes exist, so much so that people are afraid to rewrite any of these codes using modern notations. So the longevity of this standard is well assured, although it has to evolve and adapt to thread models and other models. But clearly, this seems to be a very worthwhile area for us to be devoting significant years and student research time. Okay, as a very simple illustration of what an MPI program could do, one can look at how one can integrate the area under a curve, whereby one can spawn multiple processes. So in this illustration, the slaves are asked to integrate under the different regions of subregions, and then send the integrals using a send command to a receive command, which is taken by the master process, and it adds up the integrals. So that's a general feel for how an MPI program is set up. But as soon as you write a program like this, you can see, oops, this is not in the pristine functional sequential world anymore. There are dynamic communications happening, and these are communications which name the processes to which the message is to be sent. So here it is trying to send to process 0, but the programmers are started iteration from 0. So it's trying to receive from source, but this guy is not as 1. The rank of this process is starting from 1. So there is a mismatch in terms of communication expectation. So this is not communicating from 0. So there's a deadlock. Okay. So even as simple as a program in a simple program of a few lines, one can introduce a deadlock. So this is the story. Okay, so how about taming the complexity by trying to create a simple API of 10, 20 functions and use only that, and implement all the other functions using these 10, 20? So that would be the computer science approach. Well, it turns out that the large size of the MPI is partly explained by the wide deployment base it has and the number of applications it caters to. So it offers a very broad interface of which many applications take a tenth of the functions, and it's a different tenth for different applications. So it seems inevitable that we look at the large space. Okay.
So what do you mean by out of order completion?
Out of order completion. Okay. So the idea is that it'll be introduced in a few seconds, but the idea is that when MPI calls are issued in program order, they need not finish in program order. The idea is that the fundamental guarantee that MPI makes is that of point-to-point message FIFO ordering, or called non-overtaking. So if you are sending messages to different destinations, you could afford to finish a later send, which might be sending a smaller message ahead of the earlier send. So this is a real aspect of these deployed asynchronous communications that we need to model and handle. Okay, so this is a fundamental aspect of our work, and it'll show up in many places. Yes. So there are, like I said, like Madan was asking, not just non-blocking operations, but out of order finishing of the operations we need to be modeling. And so in this space, we have to make progress by pinning on some bug classes, and that's what we did. We looked at being able to find deadlocks, such as might happen when you send to two different processes and then try to receive. Here the deadlock might happen due to buffer not being available, or misplaced global synchronization operations like barriers, or here's a feature where a non-deterministic receive is offered, and it can be matched by either this send or this send, which are both sending to address P0, the process P0. The data itself is not being shown here. So this might be a favorable situation in which the send from P0 matches this wildcard receive, when this send from P0 matches a receive expectation from P1, that's all going fine. But on a different cluster machine, if you port this program, what you might find is that because of the speed, this send offer is matched early, in which case a deadlock can happen when the other send is attempted to be matched because it's not coming from P1. Okay. So this is called a communication race, although there was a non-deterministic. And you might ask why there is non-determinism in receive, and I'll show you in an actual case study later that non-determinism in receive is a meaningful feature which we can actually use. We are interested in finding resource leaks that happen. Many objects are allocated in an MPI program and forgotten to be deallocated. So that's a thing. And we are looking for local assertions placed in the program. Okay, so we would like to run the actual code because the designers finally get value when they can run real applications through a debugger, which offers good coverage guarantees. So testing methods are notorious. There are pages, one or two page codes in MPI where you can test the program several times and never find a bad schedule that causes a deadlock. It's very easy to show that. Static analysis methods are not very widely usable here just because of the concurrency nuances, and the cost of spotting a false alarm can be, as reported in a paper by Nagapan and Patrice Godfrey in a conference last year, several months of designers' time. So we don't want designers to be burdened by false alarms. Static analysis can give you bugs in regions that cannot be accessed. Model-based verification can be used if the finite state models are creatable, but for real deployed MPI programs, nobody will give you a pristine finite state machine model that can be separately verified. So we are left with nothing but the possibility of running dynamic verification, which is actually to instrument the program and replay the different schedules, and hopefully we can contain the schedule growth. Okay, so when you embark on verification, there are a number of exponentials facing to kill you. Exponentials in the data space, symmetry space, interleaving space. So the message here is that it's reasonably clear in many cases how to downscale a model so that you represent a smaller number of processes and a smaller number of data items to work on. But it is less clear how interleavings can be similarly shrunk, because each interleaving seems to be its own beast, and so we need the tool to automatically figure out which interleavings matter, schedules matter. That seems to be one place where human intuitions are less reliable. So in a large execution, so even with 5 threads and 5 steps in each thread, one can do some simple math and find out that the number of schedules, interleavings, can be more than 10 billion if you have all these actions permutable equally with other actions. Okay, so whereas if you track dependencies in the actions, we can find that by just replaying the dependent actions in multiple orders, we can cover the kind of bugs that we are going after. So this is the intuition that is present in several techniques, and the pioneering work in this area in dynamic partial auto reduction was done by Flanagan and Godfrey in Popple several years ago. So that's the kind of approach that we were motivated by, and we want to go after such a technique. We also wanted to keep in mind the kind of dependencies that arise in MPI programs as opposed to what arise in thread programs. In thread programs, dependencies are fairly pervasive in the sense almost all interactions happen through shared memory. So the number of schedules that you need to play out can be very large. But the interesting thing with MPI programs is that for very large MPI programs, sometimes you can play out just one interleaving and be done. There is no dependency. And sometimes these wildcard non-deterministic constructs may be offered but may not materialize during execution. So in which case also we don't need to play out more than one interleaving. And when interleavings arise, it's sort of bursty, and all the processes may be involved in that non-deterministic attack on a send, on a receive. So with this kind of structure in place, we wanted, we couldn't really go after preemption bounding or heuristic searches like that. We wanted to be more exact, and that's what we were after. Yeah.
But you also model out of order
Yes,
execution.
absolutely.
So in that case, you cannot run the program, right? You literally have to recompile the program.
Well,
which
yeah, our scheduler has delaying techniques. Our scheduler captures operations and sends into the MPI runtime an out of order. It exploits the latitude offered by the API semantics in being able to execute certain commands out of order, and sends the commands only when they are sort of ready to go. Okay, that is coming in a second. So the out-of-order execution semantics is a mystery present in MPI and causes surprises to people. But knowing the API's latitude in being able to reorder, we can exploit that and assure you that such behaviors will not cause problems. Okay, that's the idea. So in fact, this example, a simple example, is going to tell us a lot about what we need to do, even for a simple 3-line example, 3-process example. So for instance, here is a simple example with a non-blocking send called MPI ISend to process P2. I'm not showing the data. And then a barrier. A barrier is sort of like a point that all processes have to arrive at before anyone can cross. And here is a barrier, and then this is a send to another process. And here there is a non-deterministic receive from any process into the barrier, and then the barrier. Okay. So what can happen in this kind of a simple program is, one might even ask, okay, there is a barrier here, so can this send ever match this receive? Because this send is written after the barrier, this is before the barrier. So in a normal shared memory sense, such a match cannot occur. But in MPI, there are delayed completions. So the timeline of execution is such that you can issue this non-blocking send. It is detached. The computation is going on. And this is issued. It is detached. It's going on. Now all processes have arrived at the barrier. So they can cross. And while these two are alive, this also becomes alive. And now a match can occur. So this is an aspect of combining non-blocking semantics and the barrier not really requiring the operations to finish. And again, all efficiency minded, because these data that may be shipped with these operations may be several megabytes, and you don't want the data to be shipped. So the weak guarantees offered by MPI are such that these behaviors should be permitted for higher performance. Now, if you look at this behavior and try to sort of do execution replay, saying that let us issue P0 send and P2's receive first, make that behavior go through, verify that, unwind the schedule, let us now issue this send and this receive alone, and go forward. That's not going to work here. Yeah.
So what's the semantics? So barrier does not have any fence semantics.
Barrier has the semantics of sometimes being able to prevent certain communications across, sometimes. So what barrier is trying to do is it tries to erect a constraint going later. So for any operation later cannot be begun unless the barrier has been crossed. Oh. So it's like a weak fence in that sense.
There's more than one kind of send and receive too. There's the synchronous kind.
Oh, yes. There are several models of send. So here we are just looking at the non-blocking kind, but we are trying to canonicalize it to this send, which can be detached. So the barrier is a mild time alignment device. And we have, of course, an algorithm in the tool, which I'll show later, which finds out functionally irrelevant barriers. So we can actually find out whether the barrier is creating any orderings more than what's present. And in some cases, it doesn't.
So without the barrier, if
you
had some other send after the barrier, that send could have actually happened, can be issued before the first send in P0.
Issuing happens in program order, but if this send happens and to an unrelated process, even this send can finish before this process. But what you have to, I will come to the detail in a second. These are like split transactions or split operations, a well-known paradigm. So the usual completion operation for a non-blocking send is a wait, which I haven't shown here. So when a wait successfully unblocks, that is when the send can be deemed to have finished. So if you put the wait associated with the send right here, then that makes the barrier a meaningful entity. So this is just for illustration, showing that the fluidity that this API offers prevents certain common tricks of replay debugging from replay. So we cannot just issue this as a piecemeal and then this as a piecemeal and hope for anything to happen. The reason being that we cannot issue P2 unless we issue this send also, because of the barrier. And when both sends are present in the system, the MPI runtime can pick up its own send and finish. We have no control over the inputs of the MPI runtime. So we need some other technique to sort of match this alone or this alone. So what we really do is we know that there is no completion obligation between the send and barrier. So we actually in our system will issue the barrier first and delay the issuing the sends. We collect the sends and keep it in the system. So we are trying to discover the most number of sends that can attack the receive, and that's why we can delay things till they cannot be delayed any further. Once we know that, we figure out these two sends can match, then we dynamically rewrite instructions. So this is going to be from P0 instead of from any. So that, when issued, forces a matching. And then you can unwind the execution. This is a stateless search. And then coming forward, we can rewrite this to receive from P1 and then issue. So this actually is, in a nutshell, what we do. We start the execution. If the operation is not at a blocking call, the scheduler simply collects the non-blocking call and lets the execution continue till the process comes to an ordering point in one process, then it switches to the other. So once it delays till it cannot further delay, it knows the full extent of the non-determinism, and then it computes all the possible choices and then replays. Okay. So this is how it goes, but let's try to get some understanding, formal understanding, because this is all very operational, but we'll go to a precise model. So the main correctness guarantee that MPI gives is very weak. It's non-overtaking. Between 2 points, when you shoot 2 messages from A to B, they arrive in the same order. There's no other guarantee. So if you can exploit that understanding and set up a suitable ordering that is to be satisfied, that gives you then a good understanding of all the schedules that are permitted between the MPI calls. It's also assumed that the C code that you write between 2 MPI calls do not exploit the particular ordering of completion of the MPI calls, because the MPI calls, even though they appear in program order, may not complete in that order. So we are making some assumptions about not relying on the particular observation being made. But that is unavoidable. So let us understand a little bit. So I'll just look at 4 operations to make life simple. Let S stand for non-blocking send. Let W stand for the wait operation for that send. Let R for non-blocking receive. W also will be a wait for the receive. And let B stand for barrier. So then this is how the timeline of send or receive tends to look like. You initiate from the API the send, and the call returns. But then there are further events associated with the send or receive that are still happening. And these other events could be that the send or receive finally finds a match between other send, a complementary send or receive, and a complete event, a completion event, which says, I have voided, if I am a send, I have sort of drained my memory into the system memory, so I have completed my memory obligations as far as the send goes. Okay. So here's how, and the wait and the barrier are, I'll go through it in some more detail. And the wait or the barrier are blocking operations, which means the API calls go in, and then when the call comes back, the full effect of wait or barrier have occurred. So send with, this is going to get a little bit interesting, but let's go through it, and we'll soon abstract all this detail. And block a send where a system provides ample buffering, meaning the send where the system has enough buffer pool allocated, sort of goes like this. You issue, then the call returns, but immediately the system has drained your memory so that your memory is usable again. So that's when the send is deemed to have completed according to your memory observation effects. But the send may not have found a match. The match may occur later. But now if you run the same send in a system which is constrained, the runtime doesn't have much memory, then you issue the send comes back, and then the execution sort of blocks because the send has to find a matching receive to drain the memory as a process-to-process copy, not a process-to-system-to-process, which is permitted in the earlier case. So then the timeline might look like this. So the general effect is that when you issue a send, you supply a handle, and then the wait call uses that handle. And when you nest the timelines of a send and a send call goes in and returns. The wait call happens thereafter. Then at some point the send matches, and then both complete. So this is, all these are good indications of what goes on, and these events exist. We don't know how to exploit all these events. We can't even observe these events. So what we have created is a simple model called a completion before model. A completion before relation can be defined as opposed to the program order relation, and a completes before relation is a weakening of the program order. So that's the way in which we are going to set up the computation of an MPI program. So here's how the intra completes before relation, which is the completes before obligation within a process, can be modeled. Suppose you have 2 sends that are sending to the same target, then their intra completes before relation respects the program order, because the non-overtaking guarantee is what we need to guarantee, so they are shooting to the same target. So we cannot allow the memory effects of this send to appear to have completed after the memory effects of the second one. They have to appear to have completed in the same order. So this is why intra completes before respects the non-overtaking, supports non-overtaking. Now if you send it to different targets, then there is no such ordering. So this is where the intra completes before ordering can be weakened. So a good example is send of 1 gigabyte to P1 and send of 1 byte to P2. We should allow this to appear to take effect early in an efficient system. Receives have similar guarantees, non-overtaking guarantees from the pull side. The receives pull from the same source, then they have to obey the non-overtaking, whereas when they are pulling from different sources, you are not going to violate non-overtaking if you allow the completion orders to differ. I won't go into other details, but basically what we have done is to define completes before ordering for the particular events that have been initiated in an execution. And modulo those that completes before, we can do analysis on which points we can delay things and which we cannot. If I'm appearing to hurry, please stop me, but I'm hoping to come to a point where I have given a feel for how we have modeled the various small programs. Then I'll even give a slightly larger program and its animation in terms of the execution. So that way, at that point, hopefully, you can bridge the understanding. And then I'll actually run a tool demo and show you other details. So let's now take a simple, go back to the original program that we were baffled by, which was a send to P2 and then a barrier and a send to P2, and then receive from any and barrier. So why did that program not execute the way we thought it should? If you plot this completes before graph for this program, or build the complete before relation, there is no completes before obligation between send and a barrier, but there is an obligation for every successive operation after the barrier. So this is the situation. So clearly, at this point, we can see that these two events are concurrent with this receive. So that's completes before is going to be our handle to define concurrency. When can things be co-enabled? So this notion of co-enabled is taken to be granted in a standard serial execution, sequentially consistent kind of execution system, whereas we need a better way to model co-enabled in our system. So the long story short is that there are going to be an intra completes before and inter completes before, and we build this completes before graph while we execute forward. And whenever we discover that two events are not connected with the completes before path, they are concurrent, and you need to be aware of that. And our tool actually builds this understanding, and it will even show it in the GUI how the completes before graph looks. So the scheduler should know that. So that's what it is. So two actions are co-enabled if and only if there is no completes before path between them.
So how is this different from having a FIFO channel between any two processes? So what you're giving is a non-operational way to get to the same effect?
Largely so, I would say. The implementation is that of FIFO channels in a sense. Yeah, there are tag lanes which allow you different priority lanes for communication, but barring that, it's an operational way of looking at FIFO-based communication. Yes. Right, and there is a FIFO that there. The idea is that the blocking nature of processes forward progress is affected by the residual space. So there is a FIFO of the system, you can say, for each process that copies out into some buffer pool of the process copies out into FIFO of the system, and that FIFO can be arbitrarily small or large in the system. The real brittleness comes because we need to verify for a controlled environment and then be prepared to deploy this program for any environment. So another feature of MPI, which I'll come to if I get time, is you can have a deadlocks when the system buffer preserve is not adequate, which is well known. You are trying to push into FIFO that's not there. But MPI, because of this combination of features, can deadlock even if you add buffering. This is a slack inelastic system, which is studied in some esoteric circles, but that's another point of brittleness. Too much buffering is also bad. So all this has to be modeled carefully because we have a. So it's well known that in any language which uses channels and non-deterministic commands, you can add slack and get into trouble. That's sort of hard, easy to believe, but we have to have a good technique now to enumerate all the slacks that are needed, and we have a very efficient way to enumerate all the slacks that we can model. So we do tessellate. So again, long story short, if this message is lost, the final algorithm that we are sort of in the act of writing up and getting ready is we do the normal interleaving reduction and tessellate with that the slack enumeration reduction. Both phases are going on. Okay, so that's the back to where we are. So this is why these are concurrent and you can issue them. Okay. So what we need is a good way to define all this. We need to define some operational semantics that tells us what's the full execution space of MPI. And then ideally it will be nice to have a specialization of this operational semantics that tells us what's the reduced execution. And that's easy to set up once we have all these notions. So what we have is 4 rules from the process side which injects what we call communication records into the runtime. So whenever a process executes an MPI command, it makes an MPI communication record, puts it into the runtime. So there are 4 rules: process send, process receive, process wait, process barrier. Then the runtime itself is a reactive system that picks up these communication records and does things with it. It matches, sends and receives, it finishes up a wait and so on. So there are 5 of them here: runtime, movement, actions. So we have a page. This is the best it gets in this area, at least. We have 2 pages that sort of tells you everything about MPI as far as buffering, non-buffering, progress, through very precise operational semantic rules. And then you take those rules and execute them in a certain priority order, and that's our interleaving reduction. This is exactly what we do for containing the interleavings. And look what we do. We run all the process injecting communication record actions with the highest priority. So whenever we can do this process inject a communication record, we allow the process to inject a communication record and keep moving forward. We're not blocking the process. At some point, all the process actions are finished. Now the runtime has to do certain things, but we constrain the runtime to do only deterministic actions. So delay the non-deterministic actions till you cannot. And then at the very last gasp, we allow the non-deterministic receive match, which is what this rule shows. So this skewed priority execution of what we started with gives us our reduction. And we can show that all this is obeying the classical ample set conditions or persistent set conditions, and we get a sound reduction as a result of this. And so now 2 more mini lists. I don't know how much I'm doing with the time. Why? 10, 15 minutes. Okay, I'll be okay. So a simpler example, a slightly elaborate version of the earlier example, we find that these actions, the barrier actions, are concurrent and can be the highest in the priority order. So we pick them up and fire it. Once the barrier actions are picked up and fired, then the highest in the priority order is this receive, which now selects, hey, I like this send. So this is the matching of the send that occurs. This send then selects the receive and picks up. All these are higher priority rules that fire. And then they are completed. And then that allows this action to complete, etc. And then, so this is one more. This is how the tool looks like. The tool itself is an MPI program plus interposition layer, and the executables are compiled, and it's a push button tool, which I'll show in a second. The scheduler that injects messages. So here's this example is enough. If you keep the mental progression of what is happening here, this is what we do. So given this program, how does our tool work? Picks a process, say this process, and fires its operation to the runtime. The runtime notes it and says, you're not a blocking call, so give me you're next. So then it comes here and says, fire that. And then the system says, you are at a blocking call. You are at a strong ordering point. Anything later is completes before ordered. So switch. And at this point, it gets an operation. It hasn't issued the receives and so on yet. So it says, send me the next. I haven't issued it. Then it comes here. Then it again notices this is a barrier, so ordering point, so switch over. So then it sends the barrier. So at this point, it notices that the barrier is full. All the processes have arrived at the barrier. And there is no completion order obligation between what occurred before and the barrier. So let the barrier go first. So the runtime actually sees things carefully rearranged according to an allowed semantics. So the reordering, the weak completes before is exploited by our scheduler. And then the execution moves on. All of them let go. And now it gets this schedule comes back here. This is the wait for that send. Now we are building the completes before graphs, so we need that information for scheduling. And then that is an ordering point. The wait is a blocking call. So that's the large idea. So since I have some time constraints, I will tell you what goes on next. So while you execute, you will discover the full set of senders that can match this receive by delaying the non-deterministic receive. That's what has happened. At that point, we say, aha, these two senders can match it. So who shall go first? Well, then the dynamic rewriter comes in and says, let that send go first. So it replaces that star with the P2 and then fires that. And then let that execution go. And then you will soon find that it can now find an orphaned receive, which could not be received from 2. There was nobody willing to send to this process. Its send got matched there. So, okay. So you have to sort of this is an execution of the operational semantics as applied to this program. Okay. So why don't I show you some actual look and feel of what this whole thing is going to do. Okay. So we have implemented this tool for several platforms. It runs under Linux, Mac, and Windows, and it can actually work for several MPI libraries. So if you take one of these programs, you can see it under Visual Studio. That's the source file. So all you do is say run ISP, and in this case it's a matrix multiplication program, so parallel multiply. And it's a concrete execution, so it even has spilled the execution results here. It has multiplied the matrices. So when it runs through, it finds errors and reports if any. So no deadlocks here. So now you can say, show me what you did. So the source analyzer window can pop up, and it will allow you to step through the interleavings. And then you can say, walk me through the interleavings of how the communications matched. And it pops up enough windows to show all the process ranks. You can lock ranks, process lengths, and step through that. So you can execute till you find issues. This debug button is partially implemented. It's only 2 days old. I won't press it till the end of the talk. But if I press the debug button, it is able to cut into the Visual Studio debugger at that point. And then you can engage the Visual Studio debugger at that point. So this is how it'll go. But now you can actually obtain more information, insights. You can say, show me your message matchings that occurred. So there's another GUI, and it tells you for that execution all the send receive matches that happened in that execution. And now you can say, show me what completes before relation that you executed this schedule under. So you can say view intra CB or view inter CB, view both. So it will at this point tell you the completes before relation that it has computed for those nodes. What this will tell the designer is you can expect anything that is not connected with an arrow here to have been executed in either order. And so if you don't understand your bugs, you can deeply introspect the completes before relation and understand what happens. This has a gazillion bells and whistles. I won't show you. You can show the source code and so on. So this is what it happens. And now if I take open project solution. So this is an optimized version which now allows wildcards to be meaningfully exploited. I'll tell you how this program works, but this has a program with the wildcard receives, and whenever wildcard receives are introduced, you have to track non-determinism, and it actually finds that this execution produced several interleavings. A 4-process execution produced maybe 18 interleavings, if I remember the number. I don't want that. So 18 interleavings, and then you can step through the source analyzer, etc. So you might ask whether these many interleavings are important for this program. Well, theoretically, yes. All the send receive matches might supply different data, and based on what your data you supply, the computation can branch differently. But in this particular case, there is a higher level symmetry going on, so you need not have multiplied the matrix 18 times, and we can probably go after that. So a lot of students have done a lot of fine engineering in this project. It's a huge effort of the scale that I had never done in the academic institution. We can actually support multiple platforms, multiple libraries, and The best results we have are we can take a 14,000 line parameters hypergraph partitioner, and it checks it in a few seconds on an ordinary laptop, and no non-determinism manifested in its execution. What else can we do? We have taken codes and found deadlocks in them, and some of them are benign deadlocks. But we are after several case studies, and giving several tutorials is also in the card this year. So I'll give you an illustration of how a programmer might program an MPI and use this tool. Okay. So suppose you want to multiply two matrices. One algorithm is to broadcast the matrix B to all the nodes, and then send the rows to different processes, and the processes do their own row times the matrix multiply. This is answers in parallel, and then receive the answers. And then if there are more rows than the number of processes, you do it again and again. So a program will start with initialize, declare the number of processes you have. Then there will be a phase which broadcasts the matrix. Broadcast is sending the same array to all the slaves, and there will be a matching broadcast, so the matches have to pick up in all the different process ranks. Then there will be a send receive pipeline where these rows are being sent and these are being received. So this could be a blocking send, blocking receive, blocking send, blocking receive. The next iteration we will make these non-blocking calls so that you can pump the send and then come back, and before the next send is pumped you can put a wait and then pump it again, so it becomes a software pipeline loop. And then finally, when you receive the rows back, who do you send work to again? Is it the first thing that got computed, or is it whoever completed first? And if you follow the whoever completed first model, you get non-deterministic receive as a natural programming method here. So you can say the first winner gets the next work. So that's how the code looks like. So you can receive from the first processor back to the first processor, send it back to the first processor, or you can say receive from anybody and then send more work to that process. And then you can use a non-blocking operation, saying that you just need to wait before the previous send finished and then issue the next send. So you can set up delayed sending like that. Yeah, I did this Visual Studio demo again. In the few minutes I have, what I'll give you is, I'll tell you why system buffering is so important to model. And this could happen in any distributed system, message passing system, with non-determinism and other things. And so the idea is that when you have a program with send wait like that, it is normally expected that this wait operation is a blocking call, so there is a completes before ordering that it puts on this send. So notice that even though this send is sending to P1, this is sending to P2, by that alone you may have said these things could happen in different orders, complete in different orders, but because of the wait call, the completion is forced to occur in program order. Okay, now let's focus on this edge. What happens if I add buffering? Suppose the system has a lot of buffering, so that it sort of takes this send message immediately into its memory. So when you have that happening, this wait command, whose obligation is only to notice whether this send has copied out its memory, is like a no-op. This wait sort of says, I'm done. I have noticed that this send has sent its memory away, sent its data away. So this completes before edge vanishes if the system has plenty of buffering. So this is the buffer-induced completion before weakening. So just to summarize, in this example, the completes before respects program order if the system has no buffering. The completes before doesn't respect program ordering, need not respect the program ordering if the system has plenty of buffering. This has consequences in an interesting situation which is portrayed here, where initially the completes before graph orders this send with respect to this receive. So while this receive could have taken data, receive occurring in P2 could have taken data from anybody, and this send is sending to P2, these guys could not have matched because they are completes before forced. But now if you add buffering, so only that match is allowed. So this non-determinism doesn't matter if this completes before graph is built. Now if you add some buffering here, then this completes before edge breaks, and now there are two attacks on that wildcard. So this is the non-local effect that adding buffering to one send makes a butterfly effect matching of some receive. But the thing is, this is not as scary as it looks. We have handled this. So the naive approach would be to take every send simulate zero buffering, ample buffering, run all the exponential cases. And that's not what we do. What we do is we run one interleaving without any buffering, build a completes before graph on the side, and analyze that graph and find an optimal allocation of buffering for various sends, and then replay. And we continue like this till the enough places have been buffered to make this kind of deadlock show up. So the zero buffer execution initially is to eke out the head-to-head deadlocks, and the full buffered execution is to eke out the too much buffering deadlocks. And that is being written up. Well, I think I dumped a lot of information on you. Hopefully you get a sense of where this is going. So the work is, the issue is that we are wedded to dynamic verification just because it seems to cut into where the designers like to be. And already we have a payoff. There's another multi-core API called MCAPI for handheld phones or PDAs. It's a lightweight message passing plus threading library that has been being standardized. And we are able to apply many of our techniques. So there's a tool under construction. And if you look at the plethora of tools available in this area, there are the chess tool, the modest effort, and we have an effort for the thread programming verification, and we might branch into MCAPI verification. So the idea is that we need to, I don't know where to publish all this work. That's a slight worry. Model checking is a thriving area, but it has become, the engineering of these dynamic verifiers should get a good outlet. It'll be nice to have a meeting, maybe in Darkstool or somewhere. Okay. So engineering dynamic analyzers can be greatly facilitated if the API designers are mindful of the constraints of building a dynamic verification system, and there are several opportunities for user interface design that are only being exploited. So, okay, so I went maybe slightly over time, but thank you. This was a pleasure to introduce the talk. Okay. Questions? Sarvani is here, so she can answer. She's, I would say, after Robert, she just took over the MPI work and brought us into the dynamic verification land. And yes, go ahead, Patrice.
So what is the feedback that you got from the MPI community?
They are welcoming us like anything. This is the best part of our whole experience. So when we started verifying simple MPI locking algorithms, we were modeling in Promla and showing 20-year-old kind of verification technology in action. We found some bugs and got a best paper award for the first paper. So we said, this is good going. So we were actually working with the engineers at Argonne, and they are co-authoring many of our papers. And that community is welcoming of this research. And PPOP, Parallel Principles and Practices of Parallel Programming, is a community which is, again, liking the applied nature of this work. I'm sure, I mean, we got a CAV paper out of it, so that was good. But it'll be good to inform more communities, on both sides, yes. The usability of this tool, well, we have textbooks examples worked out as tutorials, so hopefully we'll influence the pedagogy. But barring that, the highest, largest applications of MPI are happening in situations where they have 16,000 processes and huge data sets. And there they're running into bugs that are in the MPI library and not in the user program. So we need to find ways to get there. Yeah. Yeah.
So now that you've done this, are there ways that if you were designing MPI, you would design it differently?
Yeah, well, yeah, you want to say something?
I think there is a reason why they've designed it that way, because it's for more performance critical applications. I think they have done it after a lot of thought. So I don't think it would. If I wanted to make verification easier, I would have made barriers the most stronger points.
Yeah. There is some deprecated.
That's the reason why they have done that.
Yeah. It's well thought out to a large extent. They're kind of thinking of deprecating MPI cancel, which is canceling a message that has been sent and so on. So, but it's a large effort. I mean, Al Geist told me that there are MPI applications whose code is so mature, giving 6-digit precision, atmospheric modeling, and so on, such that nobody will even touch those codes. So its longevity is importance is known. The thing is, the MPI is spreading.
No point finding bugs in the code.
Yeah. Oh no. No, but people still try to port it to new platforms, and then all these schedules that never showed up show up, which throws them into big confusion land. They are worried about messages copying, using up memory by creating copies. So they are trying to marry threading into MPI. That's where I would make a change, because now if you have threading, threads calling MPI, there's no notion of a thread rank. So two different threads could be making MPI calls, and oops, the wrong thread picks up receive. This can lead to such brittle code, which if you see the code or a page, you wouldn't know what is going on. But people are trying to get some traction there. Yeah. Well, tools available. So I would like to encourage. This is my serious effort in understanding MPI, and I did several versions of this matrix multiply. It's a lot of fun. And one student who I have hired recently is trying to measure the performance of this code on large clusters and so on. So he's even pushing the raw performance of ISP to large matrices and so on. So I don't know whether that needs to be shown, but I have his write-up. Okay. Yeah, thank you.